Kunal, myself Dr. Praveen, Associate Professor in School of Computer Science and Artificial Intelligence, SR University. Today, I will explain binary search trees in data structure, binary search tree properties and search operations, and min-max and successor predecessors, and what are the best case and worst case analysis to create a binary search trees. Okay, now coming to what is binary search tree, why we learn binary search tree, what are the before what are the concepts we have in binary search tree. So first we will discuss the binary tree. Actually, what is tree? Tree is a collection of nodes. Binary means two. A root node has contain at most two childs, either that is left or right. Okay, when we are accessing the elements, if you want to create a tree, then it will take more time. So that's why we have to move from tree to binary tree. So we can arrange only two chairs. That is called, one is left, another one is called right chair. So that is the binary tree. I will show what is binary tree and why we move to binary search tree. Yeah, before binary search tree, we have a binary tree. So binary tree, you observe here, this is the, here I want to write, this is binary, and this is also binary tree, and this is also binary tree, and this is also binary tree. The concept of binary tree is root node as contain at most two childs. At most two childs. Here, there is no child, only root is contained. And here, only left child is there. Here, the second, next one is the only right child we have. A root has contain only right child. And last diagram is represented, root contains childs, that is left child as well as right child. So now when we are create the binary tree, the time complexity will increase. So that's why we are moving from binary tree to binary search tree. In binary search tree, every node can have a maximum of two children. Okay, that's why we called as a binary search tree or binary tree. A root has contain at most two childs, right? Two children, but there is no need to maintain the order of nodes bashing in their values in the binary tree. I want to click one example here. 25, 5, and 10, 30, 74, 90, and 13. We assume. Now 25 is the root node, 5 is the left child, 10 is the right child, 30 is left child of 5, 74 is the right child of 5, 90 and 13. There is no specific condition to construct the binary tree. Okay, first element is always root node. So the second element is shifted to the left side. Third element is shifted to the right side. We continue until nth element. This is in the binary tree. Suppose if you want to display 13, you want to access the 13. So first we compare with the root node. 25 is equivalent to 13, no. Then move to the left side. 5 equal to 13, no. This is I. This is called 2 into I. This is called 2 into I plus 1. So 2i. This is I value equal to 1. I value equal to now 2 into 1. Second element is not equivalent. Third element 30. 10 is also not equivalent. We move to 30. That is also not equivalent. 13. Finally, it will take how many milliseconds? 3 plus 3, 6, 7 milliseconds. 7 milliseconds. So now it will take the more time to access the elements. That's why we are moving from binary tree to binary search tree. In binary tree, all elements are arranged in the order. They arrive at the tree from the top to bottom and left to right. To enhance the performance of binary tree, we use a special type of binary tree known as a binary search tree. Okay, This is also binary tree, but here we should follow some specific condition. That condition is, if the elements are less than root node, then we can arrange the left subtree. The elements are greater than root node, then we can arrange the right subtree. This is the scenario of binary search tree. Binary search tree mainly focus on the search operation in a binary tree. Okay, search operation means we have to access the elements from the binary tree. So from this example, you observe here. Now when we are creating the binary search tree for this example, I want to write here 25 is the root node and 5 is comparing with root node, that is less than, and 10 is greater than 5. Okay, we should follow some condition. That is, first element is the root node. The second element is comparing with the root node. If that element is less than root node, then we can arrange, we shift to the left side. If the elements is greater than root node, then we can shift to the right side of the root node, right? So now binary search tree mainly focus on the focus on the search operations is the binary search tree. Okay, now here binary search tree is a binary tree in which every node contain only smaller values in its left subtree and only larger values in its right subtree. You already we discussed. The elements are less than root node, you can arrange, you can create a left subtree. The elements are greater than root node, then we can create the right subtree. The properties that separate binary search tree from the regular binary tree. All nodes of left subtree are less than the root node. All nodes of right subtree are more than the root node. Like in our previous example, this is the 25 5. I want to write again. 25 5 10 30 74. I think 90 30. 90 30. This is the elements. So our root node is the 25. Now pi is the less than root node, so you shift to left side. And 10 is the less than 25. Again we compare with the 5. Now what about 10? 10 is less than 25 but greater than 5. So you will move to the right side of 5. And 30 is greater than root node and 74 is greater than here. 90 is also greater than here. And now coming to 13. 13, this is less than, this is greater than, and this is greater than. Now this is called the binary search tree. Okay, now you want to display you want to access the 13. So 13 is not equivalent here, move to left side. So this is not equivalent, move to here. This is not equivalent, move to here. So now in our previous example, in binary tree, it will take the, how many milliseconds we have? You observe here, 3 plus 3, 6 plus 7. 7 milliseconds. Now here, it will take 4 milliseconds. We can reduce the time complexity by using the binary search tree. Every binary search tree is a binary tree, but every binary tree need not to be binary search tree. How, why? Can you justify this one? Every binary search tree is a binary search tree. Binary tree is a binary search. Binary search tree is a binary tree. But every binary tree need not to be binary search tree. So because in binary tree there is no conditions. But binary search tree we have to maintain the condition, that is the elements are all nodes of left subtree are less than the root node. All nodes of the right subtree are more than the root node. That is more than means greater than the root node. Always we should follow this constraint, this condition. Now coming to here, you observe here 8, 3, 10, 1, 6, 4. This is a binary search tree. Now coming to second example, now this is satisfied. It's satisfied because, sorry, this is satisfied because 8 is the root node. What about 3? 3 is less than 8. So left side and 10. 10 is greater than 8, so you move to right side. And 1 is less than 8. Again, 1 is less than 3. So 1 is moved to the left side of 3. And next one is the 6. 6 is less than 8, but 6 is greater than 3. Then this move to the right side, as well as 4. 4 is less than 8, then satisfied. 4 is greater than 3, that is also satisfied. 4 is less than 6. Okay, less than means that move to the left side. Now coming to the second example, 8 is the root node, okay, and 3 is okay, and 1 is okay, 6 is okay, but 10 is okay, but 2. 2 is, what about the 2? What about 2? Now 2 is the less than of 8. Yes, condition is satisfied. 2 is the less than of 3. Yes, that is also satisfied. But we move to right side, that is not correct. Okay, now the 2 is moved to here. This is not correct. So no, this is the correct. Then automatically this is satisfied. This is the binary search tree. Okay, now you are remember the point. Binary search tree is always binary tree, but binary tree is not always binary search tree. Binary search tree applications in multi-level indexing in the database, for dynamic sorting, for managing virtual memory areas in Unix kernel. Okay, based on these all, the binary search tree applications in multi-level. Multi-level, what about multi-level? Okay, we have hierarchical level, that is the single level, 2 level, 3 level, n level, right? Okay, now BST predecessors and successors. Okay, the predecessors of a node is the node which is the with the largest value smaller than the key value. So the successor of the node is the node with the smallest value greater than the root. Okay, now 2 is the root node, 1 is left side. So 33 we compare with the 33. 33 is the greater than 2, so move to right side. And again 0 is less than 1, you move to left side. And 25 and 11, 7, 12, 13, 34, 36. And now coming to here, the predecessor of a node is the node with the largest value smaller than the key value. That is called the 25 is the predecessor. So these are all the less than elements. The successor of the node is the node with the smallest value greater than the key. So now 34 is the smallest value of 40 and 36. Okay, now this is the successor. And binary search tree operations, the following operations are performed in binary search tree. One is search, another one is sort, another one is deletion. Main is the search. Okay, why we already in our previous videos we learned linear search as well as binary search, right? And coming to here, we want to learn the binary search tree operation is a search. We have to access the elements efficiently as well as effectively. First, we have to construct a binary search tree and we search elements from the binary search tree. And after, if you want to remove some elements, then we can use the delete operation. Yeah, now the binary search tree trying complexities. Such operation best case big O of log n, average time complexity big O of log n, worst case big O of n. Now insertion big O of log n, big O of log n, and big O of n. Deletion also same. In big O of log n is the best case complexity as well as average case complexity, and worst case complexity is the big O of n. Here n is the number of nodes in the tree. N is the number of nodes. How many nodes we have to insert in our previous example? See, these are the example is there. So now how many elements? 7 elements are there. Yeah. Here n is the number of nodes in the tree. Space complexity always big O of n. Okay. The time complexity as well as space complexity. Time complexity is for these three operations, best case is same. Average case is same. Worst case is also same, right? Are you follow? Yeah. Yeah. Now BST search operation. Now BST search operation, it is very easy to search the element. So first of all, one second. First of all, now we have to create the binary search tree. Binary search tree is the search operation is performed with the big O of login type complexity. To search operation is performed as follows. Step 1, read the search element from the user. Okay, read the search element from the user means we want to read the element. So read the element that is called the element is for example 25. We assume we have some example is there 25, 5, 10, some elements are there. 25. So 25 is the root node. We read this 25 for example. 25 equivalent to 25, yes. Okay, then it will return the element is uh, uh, printed on your screen. Element is found. Compare the search element with the value of the root node in the tree. Okay, now 25 equivalent to 20, sorry, here I want 25 equivalent to 25. Yes, that is the second step. Compare the search element with the value of the root node in the tree. Right. Step 3, if both are matched, 25 equivalent to 25, display given node is found and terminate the function. Step 3, that is both are matched, then we can display the element is found. And step 4, if both are not matched, then check whether the such element is smaller or larger than the node. Suppose I want to enter 5. Now 5 equal to 25, condition fail. Condition fail. Now coming to step 4, both are not matched. Then check whether this element 5 is less than 25 or 5 is greater than 25. Root node is the 25. This is the element. So then we can move to the left side. The both are matched, then display node is found and terminated. Both are not matched, check whether the search element is smaller or larger than the node. So now next one is the step 5. If search element is smaller, then continue to search the in left side. Why we move left side? Left side means now actually the when after creation of the search tree, the all elements are less than root node. All are left side. All are constructed as a left subtree. These are all less than the root node. And we constructed at the right subtree. Those elements all are greater than the root node. Okay, clear? So that's why if the search element is smaller, then continue search of process in the left subtree. And sixth step, if search element is larger than continue the search process in right subtree. We can move to the right side only. Step 7, repeat the same until we find the exact element or until the search element is compared with the leaf node. See, repeat the same means now if the element is not equivalent to the intermediate root nodes like first root node is the 25, intermediate root nodes are 5, and some other element is 30 is there, some other element is 10 is there, and next is 94 is there, 74 is there, 13 is there. So now you want to search the 13 equal to 5, no, 13 is greater than 5, so you can move to the right side. Okay, and next one is the what is the intermediate root node? 10. 10 equal to 13, no, the condition is again fail, so then we move to the right side. Okay, this is the process. And next one is the step 8. If we reach to the node having the value equal to the search value, then display element is found and terminate the function. Okay, see, when the elements are equivalent to the when the searching element is equivalent to the node, so we can return that element. Step 9, if we reach the leaf node and if it is also not matched with the such element, then display element is not found and terminate the function. Okay, This is the process of the BST search. Okay, how many operations we have? One is the search, another one is the insertion, another one is the deletion. Now these are all 9 steps are related to the search operation. Okay, clear? Yeah. Now coming to all of you, look here, look this code. 1 minute, 1 second, all of you check this code. Yeah. Now the operation is the search operation. Search operation, current node is the root node. Now while current data, what is current data? In our previous example, so 25 is the current data, right? Current data not equal to data. Data means what is data? Now we are inserting the element is 20, 13. Current data 25 equal to 13? No. Go to the, now the current data is greater than, the current data 25 is greater than 13. So go to the left subtree, current data greater than data, then current equal to current left. What is the current left? 25, 5, right? Current left, and right is the 30, I think. Now here, this is the 10, this is the 13, and this is the 974 and 90, 90, some elements are there. Okay, no, don't bother about these elements. Now coming to this example, current data. What is current data? Current data greater than data. So current equal to current left. Okay, now we move from left. Okay, again, go to the next one. While current data equal to data, what is current data? 5. 5 equal to 13? No. Then again, current data greater than, current data 13 is greater than 5, yes. So current data is greater than, current data is greater than data, yes. Now then we have to move to the right side. Current equal to current right side. Okay, now 10. 13 is greater than 10, yes. Again we move to the right side. Okay, now 13. Current data is 13. Our data is 13. 13 equal to 13, yes. This is the satisfied. Okay, if current equal to null, for example, there is no elements in your root node, so then it will be written null value. So this is the search operation in binary search. All of you look here again. Yes, is it clear? Okay. Yeah. Now the BST traversal techniques. Okay, BST traversal techniques: Inorder, Preorder, Postorder traversal, and iterative variant using stacks and level order traversal using. So now Inorder, Preorder, and Postorder. These are the main traversal techniques. Inorder means we have to print the left subtree, root node, and right subtree. This is a very important traversal techniques. Preorder, first we visit the root node, and then we visit left subtree and visit right subtree. And post order, first we visit the left subtree, next we visit the right subtree, then you can print the root node. These are all the important root level orders. And traversing a tree means visiting every node in the tree. Traversing means displaying or moving from one node to another node. Linear data structures like arrays, stacks, queues, and linked lists have only one way to read the data. But hierarchical data structures like a tree can be traversed in different ways depending on the order in which we do this. There can be 3 types of traversal: in order, pre-order, and post-order. In order traversal, first visit the root node, visit the left subtree, and visit the root node and visit the right subtree. For example, I have some elements are there: 25, 5, 30, 10, sorry, 10, 13, 74, 90. Is that right? Okay, now you print the in order. In order. Now first visit left subtree. Now this is root node to right left subtree. Is there any left subtree? Nil. Right, nil. So we can print the left subtree, no left subtree. Then you print the root node because left subtree, root node, right side. Now 10. And next, is there any left child? No. Then 13. And then 25, 30, 74, 90. Okay, this is the tree traversal by using the in order. In order, first root left, root data, and root right. Root left, root data, root right. Okay, it's simple. You remember one thing here. If you are print the in order, always elements are sorted. You have here 5, 10, 13, 25, 30, 74, 90. This is about the in order. And next one is this is the code for in order. If root equal to null, no elements. So you can return the value. And in order traversal, root left, printf, root data, root item, and in order traversal, root right. Okay, simple. You remember a root left, we move to the left child. Then we can put the root, then we can put the root right. Preorder means this is nothing but a first visit the root node, visit left child, visit right node. So 25 is the root node, 5. Now visit root node. What is root node? 25 is the root left child. Left child, what is the value? 5. 5. And is there any left child of the 5? No. So no. Then visit 10. Is there any left child? No. Then visit 13. Then left child? No. Right. And 30, 74, and 90. This is the pre-order traversal. Simply you remember class A, B. Pre-order means prefix plus A, B. In order, A plus B. Okay, this is the pre-order. Visit root node, visit all the nodes of the left subtree, and visit all the nodes of right subtree. And next, this is the code for the pre-order, void pre-order traversal, struct node star and root equal to null, return printf root item, root data or root item, pre-order of traverse of root left, pre-order traverse of root right, and post-order traversal. Now post-order is the visit all nodes of the left subtree. Simple left, root, right, root. This is the structure. 25, 5, 10, 13, 30, 74, 90. Now we want to print the post order. Post order. So now visit all the nodes of the left subtree. What is the left subtree? 5 is the left subtree. Sorry. 5 is subtree. Is there any right subtree? Yes. 10. Is there any right subtree? 13. Is there any right subtree? No. So 13, 10, 5. 25 is print last because display root data. Next 30 left root data. No left cell, 30 is root data, 74 is there, and 90 is the root data. 90 which is the root of 90? 74. which is the root of 74, 30, 25. This is the post order. So here, post order, root left and root right, and one more is the display of root data. Now this is the code for post order traversal, void post order traversal, struct node, star root. If root equal to null, then no elements in there. And post order traversal, root left, post order traversal, root right, and root item. This is the example A, B, C, D. Now you have to write the preorder, post order, and preorder tree traversal 1, 2, 3, 4, 5, 6, 7. Now you have to write one is the this is root node. Inorder, this is root node. Left child, this is left child. And root node, this is root node, this is right child. And this is the root node. And move to right side, this is the root node. So we visit left side. And next one is the visit this one, visit this one, and visit this one. So 4, 2, 5, 1, 6, 3, 7. Now what can you explain what is it correct? Is it correct? 100% it is wrong, because this is the binary. This is not a binary search tree. First of all, 1, 2, 3, is it binary search tree? No, 100% it is not correct. Okay, now we have to create a binary search tree for these elements. This is the binary tree, not binary search tree. Okay, now I want to write here. Already you know all this one. Yeah, I want to write here 25, 5, 10, and 13. Next one is the 30, 74, 90. In order 5, 10, 30, 25, 30, 74, 90. Pre-order 25, now 5, 10, 13, 30, 24, 90. Order 13, 10, 5, 90, 90. Okay, 90 and all this. Okay, this is about the binary search tree traversal techniques. Okay, thank you all. Thank you once again. Now please like this video and share to your friend circle. Thank you all.